Okay, I've got the thumbs up. Looks like we're ready for our next spotlight. Hello, I'm Barry Sullivan, Program Director for the Electrical and Computer Engineering Department Heads Association. It's my pleasure to introduce the spotlight presentation by Quanser on Building Industrial Readiness in Modern Control Education by Pasha Javid and Tom Lee. And Pasha will be making the presentation. Pasha?
Good morning, everyone. It's a pleasure to be here. My name is Pasha, and I'm giving this presentation on behalf of Tom, who couldn't be here. He's going to be here later on. So I'm glad that actually the spot and the slot for this presentation is at this time, because with the previous presentation, especially with what Ray began with, lays a great foundation and the framework needed to make better sense out of this presentation. So today we're also going to be continuing the discussion and talking about whether our engineers and the graduates of today are ready for the great challenges of engineering that are present in our society. And we are trying to address the question of whether what we're doing in the engineering departments when it comes to teaching is what it takes to get them to the point that they need to be ready to address the grand challenges of tomorrow. So we at Quanser for the past couple of decades have been trying to wrestle with this challenge, and in order to address that, we have this wide selection of experimental platforms for teaching and research in control systems and mechatronics, and that's our history. But more than talking about our history today, I want to talk about the higher level objectives and goals that we have. So a lot of you or your faculty colleagues at your universities are involved with teaching courses involving mechatronics, robotics, which with the ultimate goal being to design a system such as this, a space rover. And we start with using platforms that were mentioned earlier on, such as Arduino, Raspberry Pi, which are gaining a lot of momentum and popularity these days, to program small hobby robotic kits at the undergraduate level. And the students kind of feel the disconnect, not only the students, but yourselves and we feel the disconnect between still what happens at the programming level of that lab robot and what the reality is. So one of our challenges is to address that and to make sure that the fun of programming is harmonized with the theoretical background and academic knowledge that the students need to gain in order to be complete system engineers who are capable of being multidisciplinary enough to address all of the requirements that you have to deal with in order to design that platform, such as measurement, modeling, classic control, real-time control, and at the end, and overall being a systems engineer approaching the whole problem. So again, another way to define that problem or to define that challenge is to basically try to bridge that gap between the fun of the programming and everything else that's involved in order to get that robot to move with the mathematical background and the abstract theory that's behind it and is a very important requirement. And more appropriately for this audience, that bridge should probably look something more like this. But to define a sub-goal for ourselves before moving ahead is throughout the rest of the presentation, I want to share with you some of the ideas that we are playing with in order to harmonize the fun with the theory, because both are of equal importance to us. And throughout this presentation, I'll try to give the storyline of the life of a student coming into the school and then graduating and going out of the school. So they come into the school very curious, very keen, very excited, and they're ready to learn and basically get involved in some of the applications that they've seen so far as the real engineering challenges. And last year and throughout some of the ECEDHA webinars that we've given, we've introduced this idea that we've been playing with for a while, which when it comes to teaching controls at an introductory level, tries to address that bridge by bringing a game-looking like application into a classic control teaching lab. So I'm going to play the video if So what's important here is that not only the application looks like a game and it's very cool, but actually those two DC motors are introducing real dynamics into the whole simulation loop. And as you interact with the motors, you can see that you can affect the performance of the car. And here we have the left motor representing the speed and the right motor representing the position of the car. And the devices are acting as hardware in the loop devices in the entire simulation cycle, which is also a technique widely used in industry. And it's now being used at undergraduate level. And that's what we introduced over the past year or so, and we've been playing with. So moving ahead, before introducing this is where this is how controls was taught in undergraduate labs. There's a device, a DC motor, that was usually looked at as the star of the show. And that's what I want to argue actually throughout the rest of the presentation, that's not the case actually. So the server was the star of the show. We have some software environments such as LabVIEW, which takes charge of the control and data acquisition and interfacing to hardware. And then we feed it some abstract signals and study through that the concepts of modeling, PID, speed, position control, and all the classical control topics that come with it. So what happened with the QDS or the driving simulator example that I showed you was that we added a hardware in the loop application, and we wrapped the whole lab with this application, which is very rapidly interchangeable, and in that case was an automotive application. So not only we were covering again the classical concepts that I just mentioned, but through this addition of game controller input devices and also the automotive model, it now opens the door into a much, much wider range of applications and teaching topics that the students will get a chance to work with, not only on the classical control side, but also on things such as the main applications, sensors and encoders, the fidelity of the model, signals, data acquisition and filtering, and even human factors, because there is user interface design involved, and there's a lot of parameters that you wouldn't normally touch on if you were just teaching classic controls. Keep in mind that we are still using the same two platforms, but now instead of looking at them as the star of the show, we want to look at them as a system component of a much, much bigger system and solution that we're throwing in front of the student. So a little bit about that cube that we saw. It's basically our new DC motor control experiment that's recently designed. It's our latest technology in DC motor control, and it's designed to be affordable to equip multi-workstation labs, and it's designed specifically for teaching at undergraduate level in controls. A little bit more about that is coming up shortly. So now I want to move to the second part of the storyline, where that curious student we saw at the beginning is now starting to think. When they come and they start working with these devices, they have to think in order to get them to do what we want, what we're asking them to do. And in order to do that, again, of course, we cover all of the classic interesting control topics, modeling, stability, frequency, domain analysis, time domain analysis, and in more advanced courses, maybe state feedback, LQR control, observability, and things of that nature. But again, going back to the beginning and looking at the cube as the star of the show and as a control plant, I just want to show through this video that it actually does work, and it does what it's supposed to do as a control plant, and satisfying the objectives of a control problem to swing up and balance the pendulum, which is one of the most famous problems in controls. It does that, and that's great. And through that, as I saw, we cover a lot of material in basic control theory. But now, what if we wanted to think about the cube as a system component into that whole objective that we defined for ourselves at the beginning? What if we wanted the students to actually do a little bit of engineering? And this couldn't match any more perfectly with what Ray showed earlier on when it comes to doing engineering. And it's now time to actually introduce you to another new product, which is released by NI, called the MyRio. I'm sure we're going to hear a lot more about it throughout the conference. But when you put the cube together with the MyRio, you have this very powerful platform that is now a complete solution for systems design and not just for control teaching. This is a video from earlier last year from the NI Week of 2013, where we just wanted to prove to ourselves, to NI and to everybody else, that While the NI-MyRio is a device targeted at student design projects, graduate and master's and PhD level, it's actually definitely capable of doing computationally intensive tasks such as controlling a quadrotor, and obviously we can take advantage of its low footprint, very small power requirements, and the capabilities to throw it on an unmanned vehicle. So it's definitely great, but obviously none of us have the budget and luxury of throwing a 20K quadrotor in front of every undergrad student. So what's the next best thing that we can work? Then that's when we started putting together the Cube plus MyRio solution. But before, again, talking a little bit more about that, there's this cool video I wanted to show. This is a device on the Cube that normally doesn't come with it. It's not even designed. It's not even offered as an official product. So for those of you who are involved in controls, this is a very nice technical demonstration of observer-based control and observability. But for those of you who don't care about controls as a system, you can see that very easy with some common hardware store parts and a small magnet, we were able to come up with a completely new experiment with an existing device that was acting as our precise dynamics. We, or for that matter, a student could have gone ahead and put this together and opened the door into a much more advanced control problem that wasn't offered out of the box with the Cube. And that's the main point that I want to transfer across here. With some common parts, some creative fabrication, the students now experience a systems engineering or a design experience rather than just a classic control problem. Sorry that I have to go through this a little bit faster than anticipated because of the videos. Again, a further example, another example that shows how powerful this whole solution is by the use of rapid prototyping tools such as 3D printers, which was actually used to design that module, and come up with this next example where through a Kinect or a camera, which the MyRio is definitely capable of supporting and doing computation on, we can extend that previous example and actually control the position of the ball. Of course, we would love to use the observer because that's more challenging, but if you didn't feel like designing the observer, we could easily use this camera to also track the position of the ball and control it. But again, the control problem itself is what we talked about at the beginning. This is just meant to show that the Cube is definitely a system component, a mechatronic or robotic system component, rather than a end-user control plant. And this Cube and MyRio solution is part of a much bigger ecosystem that we are now working with our partners at National Instruments, which actually starts at a much earlier level of undergraduate studies with more simpler plans, and then extends into the whole undergraduate and then graduate advanced research ecosystem on the right-hand side with more advanced platforms and plans, which are all centered around the software framework provided by LabVIEW and our Quanser RCP toolkit for rapid control prototyping. And you can see that the whole solution spans very nicely across the undergraduate and then postgraduate V diagram as you see here. And that V diagram can be looked at as another way, now going back to the beginning of our presentation, where we talked about the classic control topics and then the modern embedded world and the systems engineering world that's happening. You can see that the systems engineering can wrap all of the other smaller subtopics that we talked about underneath in this diagram, starting at the very bottom with modeling and landing at the end with the systems engineering solution that the students can foster their thinking. And finally, the curious student who came in, started thinking, started doing, and now it's all about readiness when we're shipping them into industry from school to make sure that they're ready to tackle the challenges of engineering. And finally, I just wanted to mention that to continue the discussion with those of you who are interested, we have this focus group tomorrow morning at 7:30 a.m., and we look forward to seeing some of you there. Thank you very much.